Welcome back to the River Detective. Every river tells a story, but sometimes the story is a crime thriller. When a plastic plume hits a waterway, the police start teaching. How do you find out who did it, how much they done, and if we can prove it in a test? Today we're looking at chemical fingerprint in river and evaluating the classic dependable world of wet chemistry methods in modern environmental forensics. With me is an incredible panel where forensic scientist Dr. Maya Lin, analytical chemist Dr. Sam Pepper, field hydrologist Jordan Cross, and environmental attorney Tyler Vance. Welcome, everyone.
Great to be here, Alex. Ready to talk shop.
Thanks, Alex. Excited to defend the honor of the BK and Buret today.
Glad to be here and glad to be in there for once.
Thanks, Lex. Looking forward to explaining how all this chemistry actually holds up in the front of the jet.
So let's start with the basics. Maya, when we talk about chemical fingerprint in a river, what are we actually looking for? Rivers are exactly static. They flow, they mix, they change.
Exactly, Alex. And that's the challenge. A chemical fingerprint is a unique combination of chemical constituents, isotopes, or concentration ratios that are characteristic of a specific source. Think of it like this. If an industrial plant illegally discharges wastewater, that water doesn't just contain one pollutant, it has a specific cocktail of heavy metals, organic compounds, pH levels, and dissolved ions. By mapping that specific profile, we can track it upstream right back to the pipe it came from, even after it dilutes.
And from the field perspective, timing is everything. A river is a moving conveyor belt. If someone dump a chemical by midnight, by 6 a.m., that fingerprints might be miles downstream or heavily bound to the riverbed sediment. My job is to catch and ensure the sample reflects the true state of the river at the exact moment.
And from my side of the table, that fingerprint is our smoking gun. But a fingerprint is only useful if the methodology used to identify it is flawless. If the science is shaky, the defense throws it out and the polluter walks away.
That brings us to the track of our discussion today. How we analyze the sample. Sam, when we people think of forensic science, they often picture $1 million, high-tech instrument, mass spectrometer, automated robots. But today, we are evaluating wet chemistry. Why are we still talking about titration and calorimetry in 2026?
Because the flashy machines aren't always the best tool for the job, Alex. Wet chemistry, methods that involve liquid phase reactions without massive automated instrumentation, remains the bedrock of analytical validation. Think of classic volumetric titrations for dissolved oxygen, gravimetric analysis for total suspended solids, or calorimetric assays for nutrients like phosphates and nitrates.
Well, isn't it slower?
It can be, but it's exceptionally robust. Wet chemistry gives us direct stoichiometry. You are watching a chemical reaction happen right in front of you. High-tech instruments require extensive calibration curve, and they are prone to matrix interference, meaning other junk in the river water can confuse the machine. Wet chemistry methods are often more selective or easily adapted to isolate the specific analyte we care about.
Sam's right. In forensic analysis, we use wet chemistry for screening and quantification of major indicators. For instance, determining the chemical oxygen demand (COD) or specific functional groups using classic wet extractions tells us the nature of the pollution before we even inject it into a chromatography system. It narrows down the suspect list.
There are also a logical angle. I can take a basic wet chemistry kit like a portable calorimeter or digital saturation setup, right to the riverbank, getting the real-time data on pH, conductivity, and dissolved iron right next to the suspect discharge pipe is a game changer. It tells me exactly where to take this deeper sample.
Taylor, you have been in here. When Sam and Maya hand you data derived from wet chemistry method, how does that play out in a legal setting? Is it just going to scope at a titration compared to a high-tech computer printout?
Not at all. Not at all. In fact, judges prefer clarity over black box instinct. In environmental law, we rely heavily on standardized approved methods, like those laid out by the EPA or the ISO. Many of those gold standard methods are wet chemistry protocols. Let's say if Sam can stand on the witness and say, I followed EPA method 310.1 precisely, the color change occurred at exactly this volume, and then confirming the alkalinity, that is incredibly hard to dispute.
The keyword there is a chain of custody and reproducibility because wet chemistry relies on fundamental chemical laws. If another independent lab replicates SAM steps on a split sample, they will get the exact same result. There's no proprietary software algorithm hiding the data.
But we do have to be honest about the limitations. Wet chemistry generally has a higher detection limits than instrumental methods. If you're looking for parts per trillion of a highly toxic pesticide, wet chemistry won't cut it. You need gas chromatography mass spectrometry for that. Wet chemistry is best for macro fingerprinting, finding the bulk characteristics of the scale.
And we can't forget the human error. Wet chemistry requires a skilled hand. If a technician misread a meniscus on a burette, or there cross-contamination in the field or during a liquid extraction, the fingerprint gets smudged.
Imagine a local river suddenly experience a massive fish kill. How do you feel frontline forces using this method to solve the mystery?
Okay, first, I'm racing to the scene to map the plume, and I'm doing fine titration for dissolved oxygen. If the oxygen is near zero, we know we are dealing with something high in organic matter or a reducing agent. I grab a sample upstream and at kill site and downstream, sealing them and hermetically.
Then they land in our lab. Sam and I run a battery of wet chemistry tests. We check the pH, total hardness, and use colorimetry to look for sudden spikes in ammonia or cyanide. Let's say we find massive levels of hexavalent chromium through a diphenyl carbazide colorimetric method, a classic wet chemistry test. That instantly points the finger at metal plating or tanning industries upstream.
And because we use a well-established calorimetric method, we can quantify exactly how much chromium was in the water per liter, ensuring our reagents were fresh and our blanks were clean.
So once they gave me those numbers, I look at the permits of the factory stream. If let's say factory A is permitted to release a tiny fraction of chromium, but our river sample shows concentration of 100 times higher, then I will file for an injunction. In court, I present Jordan's field log, Sam's wet chemistry data sheets, and Maya's forensic report, tracing the concentration gradient back to the factory A's drainage ditch. It's game over for them.
So that tracking the environmental criminals require a perfect blend of muddy bridge, courtroom strategy, and the enduring reliability of classic laboratory chemistry. High-tech tools might get the headlines, but wet chemistry remains the foundation truth teller of environmental forensics. Thank you, Maya, Sam, Jordan, and Taylor, for pulling back the curtain on how we keep our river clean and hold polluters accountable. And to our listener, Q&I on your local water. Until next time, stay curious.